now that I've decided that there's no shortcut or really direct approach to getting what I want here in this problem, and I'm going to just slug it out. I'm going to start with this, one of the simpler of the joints. That happens to be the reaction area, because I only have two members that frame in, and the only non-zero reaction is this vertical one. And I can tell right off when I look at this that I can guess pretty accurately that the only way this is in vertical equilibrium is if AH, the diagonal, has a vertical component acting downwards. And note that that means it has an X component that acts to the left, so AB, the only other member force that's in that free body diagram, has to be acting to the right. Conceptually, I've already just figured out what's going to be happening here, but from a numerical standpoint now I'm going to go look at, okay, sum of forces in the Y. Let's take downwards as positive, so I'll have a minus 125 plus the vertical component of AH, or AHY. That'll be equal 0. That gives me the trivial answer that AHY equals 125 kips. Right now, of course, at some point I'm going to want to know that full force, and remember that that member is at the 4, 5, with 4 on the vertical, 5 on the horizontal, square root of 41 for the hypotenuse. Right? So the actual AH is going to get increased by then our square root of 41, the hypotenuse length, divided by 5. I'm really just, divided by 4. So depending on which angle you're looking at, that's either a cosine or sine, but we want that vertical component in relationship to the hypotenuse. So that'd be 125 times 41 square root divided by 4, or 200.097. So that means that AH is equal to 200.1, and our units are kips. And note it is pushing on the joint, which means the joint is pushing on the member, or in other words, it's in compression. Okay. Now likewise then, we can come along and we can look at sum of forces in the X. We can take to the right positive. We get AB, and then minus the X component of AH. So that means that, of course, AB equals AHX, and AHX is going to be equal to then 5 over square root of 41 times AH, or 200.1, which is really 200.0976. I still have that in my calculator, times 5 divided by square root of 41, and we get 156.25. Notice these positive numbers we're ending up means that we guessed correctly about what was happening with that member force. AB is pulling away from the joint, so that means the joint is pulling away from the member. In other words, the member is in tension. Right, so now we could go on to the next joint, but since I've already kind of decided I'm going to have to do the whole doggone thing here, then I'm going to go to the other reaction, and I'm going to say, all right, fine, I can do almost the identical situation here, that EF has to be pushing down on the joint to equilibrate the vertical reaction of 75, and that means DE has to be pulling away from the joint to, in terms of its X component. The equations then will work out that, let's see, we'll take then upwards is get 75 minus EF times, and this time I'm going to just, instead of saying EFY, I'm going to put the numbers directly in here. 4 over square root of 41 has to be equal to 0, so therefore EF is going to be equal to 93.75 kips. You'll get a plus number out of that equation. That means we guessed right, and that is shown in compression, squeezing on the joint squeezing on the member. Right, and then we'll go to the X component here, and we'll have DE in the opposite direction, so minus DE plus EF times 5 over square root of 41 is equal to 0. Substitute in our 93.75. Why do I think that math is wrong? Because I think it is wrong. So let's double check it here. Solve that first one. We get 41 square root divided by 4 times, you got it wrong. That's 120.056 I'm going to keep that in memory, so I'll write it down 120.1. That is right that it's in compression. And then we will multiply that times 5 divided by 1 square root equals, there's the 93.75 that I was erroneously reporting before. And that's in tension. Okay, so we've got our two of our members here at this joint. We found 2 at the other one. That was at the other end of the structure. And now I'm going to start feeding this along. All right, so I'm going to flip back here for just a moment. We've discovered that force, and so that means if we know one of these and we know it at the other end, flip it around, right? And so that number happened to be, what was it? That was the one I got wrong, 120.1, and then this bottom one, 93.75, right? Pull that around to there, right? We do the same thing over here at this other side. Okay, that was diagonals was in compression. That was at 200.1, and then the bottom chord member was at 156.25. Take it to the other end before we do anything. Okay, so that's sort of our summary sheet that we've got going on there. Now, we go back and say, all right, well, then we just discovered DE was in tension at 93.75. That's all we know at joint D. But note, now this is a real trivial one. We got a 90-degree angle going on here, what I call a T joint. And if we sum forces in the vertical, it means that we only have DF, and it must be equal to 0. And so, bam, that thing is 0. And if it's 0 at one end, doggone, it's 0 at the other end as well. Equilibrium demands it. Doesn't matter that other members into the other end of the member. Right? And then the simple trivial equilibrium here is that G, when we go look at sum of forces in the X, to the right positive, we get 93.75 minus CD equals 0, so it's almost trivial. Here CD is going to be equal to 93.75, pulling away from the joint, so therefore it's in tension. Okay, now when we, before we go too far, let's go back here and put our summary forces in there. Keep track of everything we've discovered so far. Okay. And, ooh, look at that funny thing that's going on here at joint F. We found one of the members to be a zero force member, and so if we were to use a coordinate system that was perpendicular parallel to this long chord, EF and FG, we'll call going down to the right y, x prime and upwards y prime. Note here that if we sum forces in the y prime direction, then we have no choice here but to recognize that the only thing that's there is the y prime component CF. The D was already found to be 0. FG and EF are perpendicular to y prime, so they don't contribute. We set that equal to 0, so not only is the y prime component here 0, the whole thing must be 0. We had a ripple effect that since DF was 0, and we find out that another one turns out to be 0 as well. That's an important kind of idea to pick up on. Right? It does not matter that at the other end of this member CF it's connected to a highly complicated joint with non-zero forces. These joints, this chain effect here, or domino effect, meant that that member has to be 0, period. Right? And so there's really, there is something to do here. We just found out those two were 0, so when we look at the other ones, note that all we're going to decide here is that EF and FG have to be equal and opposite of each other. We already found that EF was in tension. And that value was the 120.1 56.1 kips. And that one, well, it actually was in tension, right? Oh, I made another mistake. Holy schmoly, what's going on? EF is in compression, not tension. Right, now my equilibrium equation note didn't tell me that I had made a mistake. It told me correctly that the two are equal opposite in terms of their force vectors on the free body diagram, but it didn't tell me that I had made the interpretation of the direction of the force incorrect. So, boy, you got to be really careful about these things. I'll let you decide if I'm making the mistake on purpose, just to illustrate the point of the common mistakes that are often out there. But I have found at least a couple more forces. All right, so I know 120, 120. Ooh, I'm starting to like where we're headed here. We're getting some pretty interesting information going on. Because notice I've basically solved the entire right half of the structure. I got a portion of the left half. I got a really trivial T-joint here that we'll address in a moment. But I'm going to keep following these sort of zero force effects that we've got. Well, 1, 2, 3. I still don't know everything there. Okay. Wait a minute, I got 1 and 2 only up here at joint G. I could easily find those two. And there's something really cool and interesting about joint G that we're going to save here. Right? But I'm really also attracted to this little guy down here at B. See, I'm kind of hopping all over. Well, that's what happens in method of joints sometimes. You get drawn by a whole bunch of different things. And sometimes you got to keep yourself focused on the game plan. We've already found out that AB was 156.25 in tension, pulling away from the joint. That we found out back in step number 3. And it's almost hardly not worth writing out, but we will eventually write this all out here. What's going to happen with BH and BC is almost trivial again. We're going to be careful. We're going to write it up because, golly, I've already made a couple of mistakes here. And so BH minus 100 with upward steam taken as positive set equal to 0, therefore BH equals 100. You do need to ask yourself, if BH was not perfectly vertical, what would happen here? How would this change, if at all? Right? And then in the horizontal direction, we have that we'll have minus 156.25 for AB plus the BC equal to 0. Therefore, BC is going to be equal to the 156.25 kips. And everything is in tension in this particular case. So that's a nice, interesting, attractive kind of thing, because note what's going to happen here. We already know that CF is 0. We know what the value of CD is. It's 93.75. We know now that BC is 156.25 in tension. And we wanted to find CH and CG. That was 2 of what we were after. And I look at CG and I say, no X component to CG, but there is one to CH. And I look at the 156.25 going to the left, 93.75 going to the right. I have a net leftward movement. CH has to has a rightward component, so I can now all of a sudden guess which direction CH is going to go. And that helps things. Let's actually calculate it. We'll take to the right positive, and we'll have minus 156.25 plus 93.75. Right. And then plus CH, and that's going to be 5 over the square root of 41. To get its X component, it has to be equal to 0. And we work our way through that one. And let's see what we get. There's our 93.75, right? Minus our 156.25, right? So we take that to the other side. Becomes a plus times 41 square root divided by 5. And we get 80.04 for CH. And we guessed in the right direction here. It turns out to be in compression, right? So, it's coming down. The 100 was coming down. Oh, CG has to be going up in tension. The only way that's going to work out. And so now we'll take upwards as positive, we got CG minus 80.04 times, that would be 4 over root 41 minus 100 equals 0, and therefore we'll end up with CG equally, let's see what that works out. Still got the 80.039 in there, right? So times 4 divided by root 41. Hey, that's a nice number, 50/100. Hey, that really is 150. And so we find out that CG is 150 kips. Pulling away from the joint, so it's got to be in tension. Boy, we've done a good job of guessing which direction things go thus far.